and it is estimated to have a mass about 5 to 10 times that of Earth and an orbit ranging from 400 to 800 AU from the Sun. However, despite many searches and simulations, no direct evidence for this planet has been found so far. But what if there is another possibility that has been overlooked? What if there is a hidden planet in the Kuiper Belt itself, not beyond it, that could account for the orbital anomalies of some trans-Neptunian objects? This is the intriguing possibility that two Japanese astrophysicists have recently explored in a new study published in the Astronomical Journal. They suggest that there might be a small planet hiding in the Kuiper Belt, a region of icy bodies and dwarf planets that extends from about 30 to 55 astronomical units, AU, from the Sun. In this video, we will explore how they came up with this idea, and what evidence do they have to support it. Let's find out in this episode. The Kuiper Belt is a fascinating place to explore. It contains thousands of objects that are remnants of the early stages of the formation of our solar system, some of which are larger than Pluto, such as Eris, Makemake, and Haumea. These objects are called trans-Neptunian objects, and they have very diverse shapes, sizes, colors, and orbits. Some of them have very eccentric orbits, meaning that they are very elongated and not circular. Others have very high inclinations, meaning that they are tilted with respect to the plane of the solar system. And some of them have their closest points to the Sun, called perihelia, clustered in a narrow range of angles. These orbital anomalies have puzzled astronomers for a long time and have led to various hypotheses to explain them. One of the most popular hypotheses is that there is a giant planet lurking in the outermost regions of the solar system, beyond the Kuiper Belt, that influences the orbits of these trans-Neptunian objects with its gravity. This hypothetical planet has been dubbed Planet 9 or Planet X, and it is estimated to have a mass about 5 to 10 times that of Earth and an orbit ranging from 400 to 800 astronomical units from the Sun. However, despite many searches and simulations, no direct evidence for this planet has been found so far. Another hypothesis is that there is no single planet responsible for these orbital anomalies, but rather a collective effect of many smaller objects in the distant solar system that exert gravitational perturbations on each other. This hypothesis is based on the assumption that the mass distribution of the Kuiper Belt is smooth and uniform, and that there are no significant gaps or clumps in it. But what if neither of these hypotheses is correct? What if there is another possibility that has been overlooked? This is what two Japanese astrophysicists, Tadashi Mukai and Patrick Sophia Lakaka, decided to investigate in their new study. They wondered if there could be a hidden planet in the Kuiper Belt itself, not beyond it, that could account for the orbital anomalies of some trans-Neptunian objects. To test this idea, they selected and analyzed 14 of these objects that show unusual orbital behavior, such as high eccentricity, high inclination, or clustering of their perihelia. Additionally, they used criteria and techniques like orbital stability, orbital resonance, and orbital alignment to determine whether or not a hidden planet is influencing these kinds of objects. To test their hypothesis, Mukai and Lakaka ran computer simulations to see how the orbits of these 14 trans-Neptunian objects would change under different scenarios. They varied the parameters of the hidden planet, such as its mass, orbit, and position, and compared the simulated orbits with the observed ones. They also considered other factors that could affect the orbits of these objects, such as Neptune's perturbations or interstellar medium drag. The results of their simulations were quite surprising and intriguing. They found that the most likely scenario that could explain the orbital anomalies of these objects was a small planet with a mass 1.5 to 3 times that of Earth, and an orbit ranging from 250 to 500 astronomical units from the Sun. This hidden planet would have a moderate eccentricity, about 0.3, and a moderate inclination, about 20 degrees, with respect to the plane of the solar system. It would also be located near its perihelion, closest point to the Sun, at an angle of about 180 degrees from Neptune's perihelion. According to their simulations, this hidden planet would have several effects on the orbits of these trans-Neptunian objects. First, it would make them more stable over long periods of time, billions of years. preventing them from being ejected from the solar system or colliding with other objects. Second, it would create orbital resonances with some of them, meaning that their orbital periods would be in sync with each other or with the hidden planet. For example, some of them would have a 3-to-2 resonance, meaning that they would complete 3 orbits around the Sun for every 2 orbits of the hidden planet. Third, it would align their perihelia with its own, creating a clustering effect that is observed in the real data. These effects would not be observed if there was no hidden planet, or if the hidden planet had different characteristics, such as a larger mass, a larger orbit, or a different position. Therefore, the researchers concluded that their hypothesis was the most plausible one to explain the orbital anomalies of these trans-Neptunian objects.